So welcome back, and this is going to be the fourth iteration of our webinar that we are conducting currently with Qualcomm, titled Emerging Trends in Fundamental Systems Research. Today we have Abhikrant with us, and Abhikrant is going to talk about Hexagon DSP Architecture Overview. Just a brief introduction to Abhikrant before I hand over the podium to him. So Abhikrant is currently an engineer with more than 10 years of experience working with Qualcomm. He has experience in designing and developing compilers, device drivers, and firmware using the Hexagon DSP that he is going to talk about today. And currently, he is a member of the AI compiler team at Qualcomm. His interests include high performance computing, optimal edge processing, and compilers to augment performance. So with this short introduction, I'm just going to hand over the podium to Abhikrant. Abhikrant, over to you.
Thank you. Thank you so much, Saurabh. And hi, everyone. So in today's talk, we'll discuss mainly about Hexagon DSP, what it does to the Snapdragon hardware, and why it is such an important component in the whole ecosystem of Snapdragon SoC. So I'll use this term SoC pretty often in the presentation. So SoC stands for System on Chip, and it basically comprises of multiple processors put together on a single hardware, which is called the Snapdragon hardware. So I'd like to keep this presentation more interactive. So in case you have any questions, anything that you don't understand, it can be any basic question. I would really love if you can ask it either in the chat box or like by going ahead and asking it, since we are a small group today. And yeah, let's try to keep it as interactive as possible, as informative as possible. And at the end of the session, I want you to take away something interesting that you've learned today. So yeah, with that keeping in mind, so what I'm sharing on the screen right now is the architecture of the Snapdragon 820 hardware. Now, this is slightly older generation of the Snapdragon SoC, but the ideas will remain true even if we take the latest generation of the Snapdragon hardware. So on the screen, you can see like multiple components that comprise the Snapdragon hardware. There are multiple processors that are present on the SoC. The first one, or the master processor of the hardware is the CPU complex block. This complex block is based on the ARM architecture, and it is mainly used for doing the master control. It is the one on which the Android a high-level operating system runs, and it tries to execute, or it tries to like pass on the information to the remaining processors that are present on the hardware. So this is like the master processor. Apart from the ARM block, we have a dedicated GPU. This dedicated GPU hardware is responsible for doing all the games processing, or like all the GPU computes that we use on a day-to-day basis. Like for all the game fans out there, when you're playing your games at very high FPS, well, all those games are being executed on the GPU on the Snapdragon hardware. So apart from the GPU, we have like few dedicated DSPs. So for those of you who don't know what a DSP is, DSP stands for Digital Signal Processor, and it's a specialized hardware that is generated, or that is created with the idea of doing like computationally intensive mathematical operations in a relatively faster manner, and at the same time consuming as less power as possible. So so there are very less peripherals connected to the DSPs in general, and it specializes in performing like highly intensive mathematical operations like the Fourier transforms, or in the modern day world, when we talk about AI and machine learning, it basically enhances, or it's really good at performing convolutions, which form the basic building block of any deep learning model. So we have like few dedicated DSPs on the Snapdragon hardware. So one of the DSP is called the Compute DSP, or the CDSP. Now the CDSP, it basically is used for doing all low power compute applications, which include running your audio files, doing voice processing when the voice call is active, It also enhances, or it also does image and video processing really well. It is obviously used for all the computer vision applications that are used, or that are used by the camera pipeline on the Snapdragon hardware. Apart from the compute DSP, there is another DSP that is dedicated for the modem processing. And this modem DSP is mainly used for all the communication related work that is needed by the hardware. So the communication to your 5G and 4G networks are all the algorithms are getting executed in real time on the modem DSP. Apart from these two DSPs, there is one more third DSP, which is called a low power DSP. And this is specialized for all the sensor processing. So all the GPS, gyro sensors, any kind of sensor that you can think of, all those sensors have to be in an always on kind of a mode. And like most of the sensors have to be in an always on kind of a mode. Your mic as an which takes an input for, like, let's say an okay Google kind of a keyword, that remains always on. It cannot be powered off. So for such kind of sensors or such applications, the Hexagon DSP is also used. There are some more dedicated hardware blocks for multimedia engines. We have a dedicated video hardware block. There is a image signal processing block that we have, and there is a dedicated hardware block for doing display processing. Now, some of you might be wondering, we just spoke about audio, voice, or image processing in the compute DSP, and then we have like multimedia engines mentioned over here. Well, these are basically hardware blocks, and on the compute DSP, the processing for your video applications or image applications will happen in software, whereas there are dedicated hardware blocks which will be responsible for performing a specific application. So. So yeah, so why do we have modem DSP when we already have faster compute DSP to process information? So there are like bandwidth limitations. So let's say when the data is being transferred to the compute DSP from the CPU complex block. So the CPU complex is the master processor, and it will control the compute DSP as well as the modem DSP. Now the data bus that is connected between CPU complex and the compute DSP and the CPU complex and the modem DSP, it has like limited bandwidth. And as you know, that voice call is like the highest priority, like interrupt, or highest, it is given the highest priority. Like when you get a voice call, all your applications tend to freeze. So the idea is that since the bus bandwidth is not good enough for for the DSP to handle both the applications, that's why the modem processing is actually segregated out and it is kept separate, so that the high priority calls can be routed to the modem DSP, and like the multimedia. And yeah, mind you, like both of these, even though they might sound very simple, but there is a lot of computation that goes in doing modem processing as well as like multimedia processing. So that's why we need like two separate DSPs for doing compute and modem. I hope that answers your question. Yeah, if there are more questions, yeah, please let me know. So apart from the dedicated hardware multimedia engines, there are some security layers in the hardware, which basically try to restrict the access control of a particular top level or high level application to the low level hardware. And apart from that, we obviously have the caches, the memory management units, and the DDR, which is basically your RAM memory. So yeah, this basically computes like the broad picture or a very high level overview of what the Snapdragon SoC has to offer, and yeah, all these are very, very complex blocks that execute in parallel to ensure that our experience on the smartphone is really seamless and it is really good. So talking about, so the next thing that I'll discuss is, so in this talk, we'll primarily focus on Hexagon DSP. And even in Hexagon DSP, we'll try to talk about something called as Hexagon Vector Extensions. In short, it is also referred as HVX. So H stands for Hexagon, V stands for Vector, and extensions X comes from the extensions of X, like X of the extensions. So this is basically a vector hardware which is dedicatedly used for all the multimedia applications. And for example, like all the camera applications, they make use of the HVX hardware. The AR, VR applications, or in general, the XR applications, they make use of the HVX hardware extensively. Head-mounted displays, computer vision, video processing, all of these applications that are running on the mobile phone these days, they make use of the HVX hardware extensively. And the reason is that this hardware is mainly targeted for image and computer vision kind of applications. One of the major reasons why HVX is used for most of the software processing of all these applications is that it performs really well, um, really well, and also it consumes very less power. I'll talk about both these things in the subsequent slides, but I want to tell you that back in 2012, when all these applications were not very popular, like we didn't have camera applications to be as powerful or as good that they are right now. uh, OnePlus demonstrated like 60 hours of dedicated playback, audio playback, on the Snapdragon hardware, and they were able to achieve this only because we had HVX hardware available. If you want to do similar level of performance on, let's say, the ARM architecture or on the GPU, your battery will be drained out very fast. So you cannot sustain, the mobile phone cannot sustain for like 60 plus hours. So that is a very good example that I like to quote, which clearly demonstrates why HVX is such an important hardware block in the whole ecosystem, and why so many applications are using the HVX hardware now. So yeah, when we talk about camera applications or video applications, most of the algorithms, they make use of HVX hardware. They are HVX accelerated. So this is one example where we do the low light like enhancement in photos as well as videos. I'm sure you must be using this whenever you're clicking photographs. Whenever you try to click photos in a low light environment, the photo needs to improve the brightness and also ensure that the toning in the darker areas is slightly better, so that the image quality comes out to be really good. So all these algorithms on the Snapdragon hardware are getting executed on the HVX basically. So as part of this algorithm, we do temporal noise reduction. We try to brighten the dark patches or the dark areas of the video so that the final image quality turns out to be really good. There's one more algorithm that I have. It's called content adaptive detail enhancement. And as the name signifies, when we click an image, the raw data that comes from the sensor, the image sensor, might not be able to capture all the details. But then on top of that, we apply some kind of computer vision algorithms, which try to extract some meaningful information or try to enhance the details of the object. So I'm not sure how much of a justice is being done when you see these two images, but there is like significant difference between the original image and the image that is processed by a computer vision algorithm that does the detail enhancement, and it tries to show like features of the image really well. So yeah, I think we'll try to address the topics that we want to discuss in today's presentation. So we'll probably cover the three major aspects today. We'll do a slightly deep dive into the architecture of HVX. We'll talk about how HVX has a familiar programming model. What are the tools that are supported? What is the compiler support that is available for HVX? And then we'll talk about some use cases, like how the camera ecosystem works really well when we use it with HVX. So there is some tight system integration that happens, and yeah, we'll try to cover that as well. So yeah, I think the thing that makes HVX really powerful is the SIMD extensions. So SIMD, if for those of you who are not aware, it stands for single instruction, multiple data. And by that, what I mean is, in one single instruction, you have the ability to process 1024 bytes of data. So let's say one single instruction, when it is getting executed in one clock cycle of the hardware, you are able to do processing for 1024 bytes. Okay. Now this is what SIMD stands for. But there is an additional thing which is called VLIW, which stands for very long instruction word. Now you can read about these concepts on the internet. These are fairly generic concepts, and you will get an idea of what these are. But in case of Hexagon, there are 4 dedicated slots for doing vector processing. So what this eventually translates to is that you can execute 4 such instructions which are doing 1024 bytes of processing in a single cycle, which basically means you are processing 4096 bits of data in a single cycle, which is like a significantly higher amount of data. And this is one of the reasons why HVX is preferred for image processing kind of algorithms, because as you know that images these days are growing in the resolution. Like what used to be a norm 5 years ago was like 720p, but now we are doing like 4K and 8K kind of processing on the mobile hardware. Now, when you're processing an 8K image, you need to think like how much amount of data is being processed. And this is one of the key reasons why HVX is able to do so much work in a single cycle. And it's able to process like 4096 bits in a single cycle. So let's say if you're doing a convolution, you will be able to do multiple such convolutions in a single cycle of the DSP if you program it properly. Now, what this 4096 bits per cycle results in is you can do like 256 8 cross 8 multiply operations, or you can do 16 bit by 16 bit multiply operations. What this means is you can perform 256 character type character data type operations, or you can perform 64 short integer type of multiplication operations in a single cycle. And you can when you think about it, it's a fairly large number, and that's what gives like a very big advantage to HVX when it comes to ensuring that the computational power or it is able to sustain the computational needs of the image processing, computer vision, or video applications. So trying to dig like slightly deeper down into the HVX architecture, there are 32 such dedicated registers which have a bit length of 1024 bits. These vector registers can do like character, short integer, and integer bit fixed point arithmetic. There is no support for floating point arithmetic, and this is what helps in ensuring that the design of the hardware is really small. Like it occupies very less space on the chipset, and at the same time, because it's not doing any floating point arithmetic, there will not be any floating point instructions that will be available in the instruction set architecture. We will like there will not be any need for having a dedicated floating point hardware on the block, and which significantly reduces the power need of the hardware. Because if you have to introduce floating point hardware on the hardware block, then it basically increases the need uh, for power to be consumed by that hardware block. So since we are doing only fixed point arithmetic, there isn't a need to uh, there isn't a need for very high power to be consumed by the hardware. HVX also like specializes in some dedicated instructions which augment image processing kind of applications. So when you're performing convolution on a very big image, for those of you who have studied in your mathematics courses, you might be aware that convolution on any bigger image or on any bigger matrix is performed using a technique which is called sliding window approach. So there are dedicated instructions that are present which allow to perform sliding window approach on the image. There are dedicated lookup tables, and there are dedicated instructions which help in getting the histogram related information from the images. And histogram, as you might know, is a very important metric in analyzing and getting some features from the image, because it tells a lot of information about the image. So this is like slightly older data. Like the performance is sufficient for, it says Ultra HD video post processing, but now we are able to do even 8K kind of processing, and it is going to grow as we move forward, because the demand for better imaging continues to grow, and yeah, that's why it has to evolve, and that's part of the evolution. On the right side over here, I'm going to demonstrate like how a simple multiply and accumulate operation happens. And in general, it is called a MAC operation, multiply and accumulate. Okay, which basically means we are performing a multiplication over here, and then we are trying to accumulate the result into and storing it finally into another register. So why I'm talking about this multiply and accumulate operation is, in most of the deep learning applications these days, most of the deep learning applications make use of convolutional neural networks, and all these CNNs, in all these CNNs, the basic block is a convolution, and convolution is nothing but it is multiplication and then addition, because it is simple. In simple terms, we can call it as matrix multiplication. And when you do a matrix multiplication, you multiply and then you add the result. So this MAC operation is a very important operation when we talk about convolutions. Now, why I'm talking about this is like, you have like 1024 bits of data in one of the HVX vector. Okay, you are multiplying it with another vector, and then you are accumulating the result and then storing it in another vector of the HVX. Now, this whole multiply and accumulate operation for 1024 bits is happening in a single instruction, or in a single clock cycle of the oscillator or of the processor. Now, this, if you see, it's a it's a fairly complex arithmetic that is happening. But since the architecture is designed in such a way that it allows a single MAC operation of such large computational complexity to happen in a single instruction, we are able to scale it in such a way that it allows fairly complex and very high resolution image processings to allow such image processing to happen really fast. So yeah, I think that's a brief overview of what the HVX architecture is and how it allows very complex arithmetic operations and very complex mathematical operations in a fairly simple and a simplified manner. Now, in continuation to the SIMD model, one more thing that the hardware architecture provides you is multiple threads. And we'll try to talk about what is the threading model in the hardware. So in the image over here, you can see like there are 4 scalar threads that are mentioned, and these are the 2 vector hardware units that I spoke about in the previous slide. So if you remember, I told you that there are 4 VLIW slots. So these are the 4 VLIW slots for one HVX vector unit. Now on the hardware, we have 2 such HVX vector units. Okay, so in total, so I told you that in one cycle, you can process 4096 bits. When you have 2 such vector units, you have the ability to perform 8192 bits in every cycle, right? And since there are 4 hardware threads that are available, so this HVX vector unit, it gets mapped to one hardware thread. And then there is one more vector unit which gets mapped to this scalar hardware thread. So you still have 2 hardware threads that are vacant, or that are not available, that are not being used. So these can be used for doing non-vectorized processing, which is called scalar processing. So think about the amount of work that is being done by the DSP, or the amount of bits that are being processed by the DSP in a single cycle when you are doing multi-threading in parallel. So it is performing like significant amount of work, and that is why we're able to scale up to like doing 8K image processing or 4K image processing in almost real-time kind of a scenario. So yeah, there are 4 parallel scalar threads, and each has 4-way VLIW architecture, and they share the L1 and L2 caches. So in case of scalar hardware, the L1 data cache and the L1 instruction cache exists, and then there is a bigger shared L2 cache. Okay, and there are two HVX contexts which are controlled by any of the two hardware scalar threads, which I already told you. This vector unit gets mapped to this scalar hardware thread. This vector unit gets mapped to this scalar hardware thread. Now, every thread has 500 megahertz of processing of frequency, basically. So in total, you can get like 1 gigahertz of vector performance. And still the other two threads, which are available to do some non-vectorized work, they can also continue to work in parallel. So when you're operating at, let's say, 1 gigahertz of frequency, you can think like of the amount of work that is being done in each second. So it is very significant.
So Abhikrant, I just wanted to ask a question.
Sure.
Yeah, so the two scalar processors that are mapped to these vector units, assume that currently there is really no load which requires any kind of vector processing. So for example, if there, let's say there is no application that is running which requires, for example, image processing, right? I mean, let us say
Right.
my
Audio
yeah,
kind of
right.
application.
So what the, so like, is it possible that these scalar units can then be dedicated for non-vectorized work, or is it
Yes.
they are just dedicated for the vectors?
No, they are not dedicated for vectorized work. So thank you for asking that question. Actually, these units are all four are scalar units, and in case the HVX or some application needs a vectorized hardware, the vector units get mapped to the scalar hardware thread. So it's like a need basis. If there's a requirement, only then the vector unit gets assigned to a scalar hardware thread. In a normal scenario, when there is no need of doing any vector processing, which happens in case of audio applications, only the scalar hardware, all the four scalar hardware threads are good enough to perform the work that is needed for audio applications. And yeah, that's why only the four hardware threads get executed, and the vector units are not used.
So I guess the two other scalar units can also be used for, as you said, right, like emergency situations, like a call just comes up and then.
Oh yes,
Right?
yes, definitely, yeah.
Okay, thank you.
So in the previous slide, I mentioned that these four scalar hardware threads, they have L1 and L2 data cache connected to it. Now the size of these caches are relatively smaller, so they are not very useful for bigger applications like imaging kind of applications. So we do have, by design, we had a very big L2 cache, and that's the primary reason why the vector units are directly connected to the shared L2 cache, because it is larger in size, and hence it can prefetch like bigger images or bigger data from the RAM and store it so that it is quickly accessible to the vector registers. So in this case, like the vector units are not connected to the L1 cache, they are directly connected to the L2 cache. And yeah, I think there is like single cycle load to use mechanism that exists, which basically means that in case of an ideal scenario where there are no stalls or there is no latency involved in getting the data from the memory to the L2 cache, the processing will happen in a single cycle, in a real-time use case. And yeah, they support like the full bandwidth of the processor, which is the Hexagon DSP, whatever bandwidth is supported by the DSP data cache. The same bus bandwidth is supported by the shared L2 cache as well. One more interesting thing about the architecture is that the L1 and L2 caches are kept hardware coherent. And what this basically means is that there is no need to do like cache flush and invalidation kind of operations, which are needed to be done by some of the architectures. What that basically means is, let's say if you need some data to be available in the L2 cache, you perform prefetching of that data and try to store it in the L2 cache. Now, once the register is done using that data, it needs to flush that data out from the L2 cache. So that's why for some architectures or for some hardwares, there is a need for the software to make these calls, which are called like the flush cache flush and cache invalidation operations, which need to be controlled by the programmer. But in case of Hexagon DSP, we have tried to keep the L1 and L2 cache as hardware coherent, and this helps, or this eases out the programming model for the software developers, so that they don't need to worry about doing cache flush and invalidation operations, and the hardware itself takes care of doing these things. And yeah, this is one interesting thing. The data from the camera pipeline can be directly prefetched into the L2 cache. And I'll talk about this in my subsequent slides, where I'll talk about a dedicated camera use case. So yeah, if you have questions regarding this, please hold on for some time, because I'll cover this in subsequent slides. And yeah, one more interesting thing that the architecture supports is, or the instruction sets that they help in the for an end user, is that they allow unaligned loads, and they also allow per byte conditional loads. So what that basically means is, let's say if you want to fetch a memory address that is not aligned to, let's say, 128 byte address, and you want to fetch that data from the RAM into L2 cache, and then eventually into the vector registers to do some kind of processing. So Hexagon DSP and the vector engine allows us to get data from unaligned loads, which basically means that even if the memory address is not a multiple of 128, which means it is unaligned memory address, the data can still be fetched and loaded into the memory. And you won't see like crashes or some kind of things, some these type of operations happening. The hardware is capable enough to gather unaligned instructions. And then the same is possible even for stores. Like when you're done with the processing, the hardware is capable enough to store data in unaligned memory locations. And the same holds true for per byte conditional data. Let's say if you're interested in getting only some bytes of data from the memory, there are dedicated instructions which allow conditional loading of data into the memory, processing the data in the vector registers, and then doing the byte conditional storage of that data into the memory as well. Yeah, any questions? Okay. So yeah, I think in the previous section, we basically covered why the architecture of HVX is so good, and why it's targeted for image processing and multimedia kind of applications. The first reason is there is 1024-bit SIMD vector registers available, which allow data level parallelism. Okay, there is low precision fixed point and special instruction set architecture available. And since there is no fixed point floating point hardware available, that reduces the power consumption of the hardware. There is multi-threading in form of scalar and vector threads, which allows like thread level parallelism apart from data level parallelism. And the large primary cache, the L2 cache that we discussed just now, that allows, or that augments, the image processing and high bandwidth requiring applications to work in a very, very seamless manner. So the next topic that...
So Abhikrant, I just had like one thing in my mind. So you talked about, like in the previous slide, we talked about unaligned memory accesses, right? But yeah, like I'm just trying to understand that with vector processing, if you allow unaligned memory loads, right? It can cause a plethora of problems, isn't it? Because for vector processing, my instructions are going to be designed assuming that my data is well aligned in the memory, so that you can fetch them in bulk and then perform the processing. So this might actually cause a havoc, right? Because
you're right. You're absolutely right. So this is something that is not preferred or not recommended to the programmers. But then there are people who write an assembly and they don't ensure that the addresses are aligned. Like we have had programmers who do this. They don't know, they try to allocate memory in some region and they don't align it to a specific alignment that is expected by the hardware. And then once the hardware tries to access that memory, it tries to load data from that memory address, it basically leads to a crash. So this is basically an evolution that has happened based on the problems that we have seen with our customers who have been using HVX over the last many years. And that is the primary reason to ensure that, yeah, since it should not crash, and at the same time, it allows like seamless uh, like usage for the end user. That's the reason an unaligned load and store is supported. But you're right, it's not the preferred or suggested or recommended model of
And you
programming.
probably need to put in a lot of no-op things for because there might be some vector processor which is not doing anything,
Yes,
whereas
yes. So there are,
that's
yeah, it is possible. Yes. So there are some scalar hardware threads which might, yeah, some of these slots for which you will have to introduce no-op operations. Like let's say if this slot or this vector slot is doing an unaligned load, yeah, you might have to do some kind of no-op operations in these two slots so that the data is fetched properly. And yeah, one more thing is, let's say if the data is at an unaligned location, what the hardware does is it back aligns the address to the previous aligned address. So what happens is, like, some of the data in the vector unit will be like not will be redundant data, and the sum of the data in the vector register will be the data that is actually needed or required. So that's how the processing happens, and
got it.
that's
Yeah.
how we
It's still
implement.
inefficient, but it is at least not illegal. That is the idea.
Right. We don't want to like ensure that we don't want to. Yeah, you're
Yeah,
right.
sure. I
It's
got the
not
point. Yeah.
illegal. Yeah, it's
Yeah.
not.
Thanks. Go ahead.
Yeah. So yeah, I think we'll cover about the programming model that the DSP has to offer, and mainly like HVX. So DSP, although it specializes in performing math operations, it also has some CPU-like programming features and a CPU-like programming model as well. So for comparison, we are taking into account an ARM architecture-based hardware, and the vector unit in ARM architecture, it's called Neon. So we'll try to compare HVX with a neon-based architecture, and even the results that we have subsequently are taken into account by comparing the HVX with a neon-based hardware. So uh, so a traditional CPU, it basically has like multi-threaded programming with cache-based coherency and shared memory. So the same thing is supported by DSP, Hexagon DSP. A traditional CPU, it has SIMD instructions with vector registers. The same is supported by the Hexagon DSP. And for non-vectorized processing, there are scalar hardware registers or scalar instructions to do those processing. The same is applicable for Hexagon DSP as well. There are a traditional CPU will have a good control for mixed vector, like mixed performance of vector and scalar. The same is applicable for even the Hexagon DSP. But there are some key differences which I'll try to highlight over here between like a Neon CPU versus Hexagon DSP, and then we'll talk about what are the advantages. So as I told you about the SIMD instructions of a SIMD vector instructions, the Neon hardware has like 128-bit vector size for one SIMD instruction, whereas we have the HVX has 1024-bit of SIMD vector length, and there are 4 dedicated slots. So eventually, we are able to do 8 times better computation in every cycle when we compare the performance with the Neon hardware. The second thing to keep in mind is the L1 cache size is just 32 KB for Neon, whereas for HVX it's 512 KB. So again, it's like 8 times more L1 cache is available for doing the scalar processing and even the vector processing. There is, yeah, this is like an advantage as well as disadvantage. Like there is floating point support available in the Neon hardware, so which gives it the ability to do floating point arithmetic. But since Hexagon DSP and HVX supports only fixed point arithmetic, this ensures that the area on the Snapdragon SoC is lower, and also the power consumption is much lesser. So Yeah, with respect to an end user who wants to develop applications on the hardware, there are conventional tools and techniques that are available. There is support on Hexagon and HVX to use POSIX type of threads. So for those of you who are familiar with Linux programming, the multi-threading app like way or the multi-threading use case for on Linux is POSIX, and we have a DSP real-time operating system. It's called CURT. So the DSP RTOS ensures that the Hexagon DSP supports all POSIX-like APIs, and you can easily use your pthreads and all the thread join and all such APIs which you would have been using in any normal Linux program or whenever you're writing a Linux kernel, which does like multi-threading. There is a very good support of LLVM compiler for Hexagon DSP. We have like an in-house team that does optimizations specific to HVX hardware, and I also work in the compilers group, which specializes in doing LLVM optimizations for the compiler to ensure that the DSP gives like really good competitive advantage, and at the same time it does very good job at ensuring that the code that is generated for an application is highly vectorized in nature. There is support to program in C and C++, which an end application user would need, and there is also support to program in assembly as well as intrinsic. So for people who want to get like the extra juice from the hardware or ensure that they are able to get maximum throughput from the hardware, we do have support to support of intrinsics and even assembly level coding that can be done by the end programmer. But for people who are not familiar with with very low level nitty gritty details of the hardware, they can still program in C and C++ like the way it is done for any traditional programming purpose. So yeah, this is a very interesting thing. Like we have some pre-optimized mathematical libraries, or we have some pre-optimized computer vision libraries, which contain like most commonly used filters and algorithms. Now these optimized libraries are hand-coded assembly libraries that are developed by engineers in Qualcomm, and they're basically provided to end application developers so that they can easily use these libraries to develop like larger applications. One instance for this is like, let's say if you want to run your deep learning model, which comprises of, let's say, convolution or a ReLU operator, or let's say it needs like a softmax kind of an operator. So all these operators are pre-optimized in a library that is called SNPE, Snapdragon Neural Processing Engine, and that is available as part of Hexagon SDK, and it is available for usage by our for our end customers. One interesting thing that allows easy usage of Hexagon DSP is the ability to easily offload applications to DSP from the Android. So if you remember the first slide, I told you that there is a master processor, which is the CPU processor, which is based on ARM architecture, and that runs the Android HLOS. So most of the control flow of the applications happens via Android. Now, if something has to be executed on the DSP, Android needs to inform to DSP that, hey, this is an application, this is a computer vision application that needs to be executed on the hardware, on the DSP hardware. So it needs to offload that work to the DSP. And this is done through something called as remote procedural calls, or it's also called RPC or fast RPC. So it's like a dedicated driver which exists between the ARM processor and the DSP, and it allows like seamless communication of data as well as control code from the HLOS, from the Android or the CPU to the DSP, and it is actually used for most of the camera post pre-processing, video post-processing, and offline camera post-processing and computer vision applications. So this forms like a basic building block to ensure that all these camera, video, or computer vision applications, they're able to run very seamlessly for the end users. And one more interesting thing that we have to offer now is Halite, which is a language dedicated for image processing, and it is like a domain-specific language that is developed for image processing kind of applications. It's developed by Google, and it's fairly simple to use, and it basically eases out the work that needs to be done by end programmers in writing basic building blocks for their image processing applications. So for if you want to write let's say a filter that does edge detection, which is like a Sobel filter, then that filter, if you have to write it in C or C++, the code will be like of significant amount of lines. But if you write it in Halite, it will take like hardly 10 to 15 lines. Whereas if you have to write the same filter in C or C++, it might go to 50, 60 lines. So yeah, Halite is another offering that we have. That Halite, since it's developed by like another company, but we have added support to ensure that Halite runs seamlessly on the HVX hardware. And we have a lot of customers who are using Halite for HVX to run their models on the DSP and to run their image processing applications on the DSP. So yeah, I think we'll talk about some tight system integration. So if you remember a few slides back, I mentioned that the L2 cache is directly connected to the camera hardware. So in this block, we'll talk about some interesting system level features that allow camera applications to work very, very seamlessly with the hardware. So if you see like the camera ISP, this is the camera sensor. So the camera sensor is basically the RGB sensor of it's basically a hardware block, and it tries to capture the information that comes in front of the sensor. Now, the interesting part in this whole process is that the raw data from the camera sensor can be directly streamed into the L1 cache of into the L2 cache of the DSP. And this is what I was mentioning in one of the previous slides, that the camera data can be directly prefetched into the L2 cache. It can be processed on HVX, and then it can be shared with the camera image signal processor, which can do like further post processing on the data. But a lot of the work or a lot of hard work can be done by the HVX through the camera streaming happening directly into the L2 cache. And there are some more complex blocks, like this is the CPU complex block that I was telling you about in the previous slides, which is the master processor. And it is connected to a memory controller and a shared memory mapping unit. So these are two important blocks which basically ensure that the access to a specific application is allowed. Like a top level, a high level application like a camera application will have the ability to access the data that is being processed by HVX is controlled by this shared memory mapping unit. So that's why this is an extremely important block. So yeah, I think we'll talk slightly more on what this SMMU has to offer. So there is this is basically based out on an ARM architecture, and it's an ARM compliant SMMU, which allows zero copy data sharing between the CPU and the DSP. It basically has like multi-threaded DSP that can service multiple offload sessions. So why this SMMU is important is like it can in parallel allow multiple applications to get executed and do their work, whatever they want to do. So concurrent applications like audio, camera, and CV can run in parallel, and SMMU is one important block that allows this to happen. And how this is happening is like, see, every application needs memory. Now, what SMMU does is it ensures that all the individual applications are able to get their respective memory through something called as context bank. And this context bank you can think of as like a small chunk of memory that is dedicatedly allocated to a specific application, so that it does not interfere with the memory region of another application. And that is how uh, I mean, it might sound a very simple context, like it might sound very simple when we are talking over here, but this is a fairly complex operation that is happening because you want to ensure that a camera application does not interfere with an audio application, and a computer vision application does not interfere with the memory region of a video application. So the SMMU plays a very important role when it allocates these multiple context banks and ensures that these banks are these are very these work independently without interfering with each other with each other. And one more interesting thing that I want to share over here is, let's say if the audio application crashes because of some problem, the remaining applications continue to work seamlessly because they have their own separate context banks. Had it been a single context bank, it would not have been possible. So yeah, SMMU can also support processing of secure content. Yeah, that's another feature that SMMU does. It basically checks for appropriate permissions that a high-level application which is developed in Java, whether it has the ability or whether it has the permissions from the kernel layer to ensure that it can access low-level data which is lying in the HVX hardware. So it basically does like it acts like a security barrier, or it acts like a security protocol between the high-level operating system, which is the CPU complex block, and low-level hardware, which is the DSP. Yeah, if there are no questions, I'll go ahead.
Abhikrant, like one question that comes to my mind is, in these context banks, does this also mean that when you are basically building these applications, audio, camera, computer vision, you're actually using static addressing, that the addresses that a particular app can access,
Yes.
are they
Yes.
basically statically,
Right.
right? So it's okay. So this goes up, this whole thing flows up, that you have to go and do that at the time of building the application itself.
Right. You need to ensure that like you have dedicated space in the RAM memory, and yeah, even though that space might be very less, see, that will be physical address or physical space.
Yes.
When you convert it into virtual memory, you can
Yeah.
have almost infinite memory. So that's how it is taken into account. But yeah, there is dedicated physical memory layout that is
So the
carved out.
loading is always done in the same part of the memory. Then. That is probably
It
what is
is.
happening.
It will be deterministic. Yeah.
Okay. Thank you.
Yeah. And yeah, last we'll talk about the system level features, which takes into account the one-way coherency. So yeah, basically the bus writes from DSP will invalidate the CPU caches. So if you remember, like I was telling you that this operation, for this operation, there is no need to, the hardware is coherent in nature. But when we want to communicate between the CPU complex block and the DSP, these two blocks are not hardware coherent. So there needs to be some kind of a cache flush and invalidation operation that needs to happen. And this is actually taken care of by the fast RPC layer, or the fast RPC driver that I mentioned a few slides back. So that ensures that the cache flush and invalidation is taken care of by automatic, like is done automatically, and there isn't a need for the end application developer to worry about it. But that being said, it is the driver that is doing it, which basically means that the DSP needs to ensure that it invalidates the caches when the work is done. Also, yeah, I think basically it avoids the expensive software cache maintenance on the CPU, thus saving time and energy. So since the DSP is performing all these tasks, like there is no need for CPU to do these things, and hence it ensures that there is lesser power consumption for the whole SoC, and DSP continues to be power efficient. And DSP side obviously requires cache maintenance, which I told you, but this is handled transparently in the fast RPC software layer, and the user need not worry about it. Yeah, I think I'll talk quickly about this quality of service feature. So there's a concept of like soft partitioning or L2 partitioning. So L2 cache can be soft partitioned to regions which are assigned to different threads. So let's say, as I mentioned, like we have 4 dedicated hardware threads, and those are connected to L1 and L2 cache. Now, if some thread is getting stalled because it is trying to fetch data from the memory, then that thread is not performing any job. So what this L2 soft partitioning does is it will evict that thread. It will not allow that particular thread which is stalled to allow the L2 memory region, and the remaining threads which are doing the actual processing will be able to use the L2 cache really well. So let's say if all 4 threads were working properly, then the L2 cache will be divided into 4 equal parts, and each part will be used by each thread. But let's say if this second thread, it is stalled because it is waiting on data to arrive from the memory, then the L2 gets soft partitioned into 3 parts automatically, and thus it allows like bigger chunk of memory or bigger chunk of the cache being available to be used by the hardware threads. So that's what is the L2 partitioning that we discussed. And there are 2 interesting features again on the DSP, which is internal quality of service and external quality of service. So what internal quality of service means, there is hardware-based prioritization of memory requests, and software will just assign the priority to the threads. So what this means is like ultimately, like by software over here, we mean the RTOS, which is the real-time operating system. So the real-time operating system will ensure that each software thread gets mapped to a hardware thread, and it will assign priorities to each and every thread. Like there are dedicated CERT APIs which allow assignment of changing the priorities of each thread. And once the threads are prioritized appropriately, then they are executed or they are assigned to the hardware uh, to be executed in real time. And the external QoS means that the system level hardware algorithms can throttle the DSP traffic to ensure the system performance. Now, there can be times when, let's say, the hardware is getting heated up because of a lot of processing. So in that case, there are some system level hardware algorithms which can either increase or decrease the clock frequency of the hardware so that the incoming data to the DSP via the data bus can ensure that the performance is not affected, but at the same time, the temperature or the heat energy is appropriately distributed among the hardware so that the phone does not get heated up. So these are very important metrics, or these are 2 very important features that the DSP offers in ensuring that the applications run seamlessly based on the priority, like based on the CERT based priority, and at the same time ensuring that the system does not get heated up extensively because of some unknown issues or some extensive throttling. So yeah, I think we covered very interesting things. We spoke about the domain specific architecture. We discussed about the familiar programming model, and then in the last section we spoke about how the camera streaming interface ensures that the data gets fetched into the HVX hardware unit directly, and then it can be processed uh, very seamlessly and sent back to the ISP processor. We also discussed about SMMU. We spoke about the one-way coherency, and last but not least, we spoke about the internal and external QoS, quality of service. So yeah, I think now since we've spoken a lot about the performance improvements that HVX offers, over here we have like two graphs showing the performance of HVX versus the quad crate CPU, which is using the Neon hardware. So the CPU is clocked at 2.56 gigahertz, whereas DSP or HVX is clocked at 725 megahertz. So firstly, the frequency at which the DSP is running is relatively less. And obviously, in both the cases, the core, when we are doing this power analysis, we are excluding the SoC infrastructure or the DDR power consumed by the DDR memory or the RAM memory. So as you can see, we are running like the most commonly used image processing kernels. Like all these are pretty standard image processing kernels. And this graph shows the performance of the DSP performance execution time on DSP versus the CPU. So if you see 1x, 1x means the performance of CPU, and if the graph is above this, it means that this particular graph is, or the Canny filter on DSP is performing like 1.25 times better than it is on the CPU. There are some kernels which are performing bad when we compare it with CPU, but then there are some kernels which are performing like 3 times or 3.5 times better than the than they do on the CPU. So if we average out, we have results which claim that it is definitely 1 to 3 times faster when we want to run image processing kernels on the DSP versus on the hardware. So this is the performance chart, but this is an interesting chart where we do like the power analysis. And here, if you see, we are consuming like 4 to 18 times lower power versus a CPU. So that is one of the primary reasons why DSP is able to deliver better, and at the same time, it is consuming much lesser power than the traditional CPU. So in this graph, we are talking mostly about smaller kernels, image processing kernels, but we also have data for a full-fledged application, which is like an end-to-end use case. It's not just performing like a single very small task of doing some kind of a filtering, but we have data for a low-light video enhancement algorithm. And when we run it on the CPU, like if this is the time taken by the CPU, the time taken on the DSP is like one third of what it is on the CPU. And also when we do the power consumption, like when we try to calculate the power consumed, well, it is like 10 times lower uh, when we measure it against the CPU. So why I'm showing you this graph is because when we club multiple applications and we write them in a very optimal manner, then the chances of getting better performance at a lesser power consumption are much higher. So if we ensure that if we are using all the 4 HVX hardware threads appropriately, if we are using both vector units appropriately, if we are doing multi-threading in the right way and getting the maximum juice out of the hardware, then the results can be very good. So that's the reason why I wanted to show you these results for like a dedicated algorithm which does not just do uh, a simple filtering operation, but it does like a significant amount of workload to get good result. So yeah, I think yeah, I've reached the end of my presentation. Uh, if there are any questions, I'll be happy to take them. Otherwise, I'll
Any
talk
questions
about.
from the any questions from the audience in this case? You can also put it in chat if you want. Otherwise,
or in case you have questions, you can go back, look at the video. I know it's a little complicated thing to understand in the first go, but if you spend some more time, you will understand it really well. And if you have questions, you can direct them to Saurabh sir, and uh, he can let he can tell them to me. So
yeah, sure. So please, please, everyone whomsoever is watching it later, for example, if you're if you're watching it, for example, on YouTube, you can always get back to us, and I'll route your queries to Abhikrant, and whomsoever else is required in Qualcomm. Ravi is also with us right now. He has joined. So yeah, thanks Ravi for joining. And so anyone who wishes to communicate with Abhikrant or Ravi Shankar, anyone, just get to me, and then I'll just try to patch you guys up with them. So if there are no questions, I'd like to just wrap up this session. First of all, thanks Abhikrant for sparing your time for us and talking to us about this wonderful architecture. And thank you everyone who joined us for this session. And we look forward to having you again. There's going to be one more iteration of this talk and of this webinar, and I just hope that you guys join us again in that last talk of the series. So thank you everyone. Thank you Abhikrant, thank you Ravi, thank you everyone. Bye.
All right, thank you. It's been a pleasure. Take care. Have a good weekend.
Bye. Bye.